Hi, am I audible clearly?
Yes, sir.
All right. We'll start in a bit. Let's see if more people join in. In a couple of minutes, we'll start. This will be the session for week 9. We'll go over the concepts covered. And then at the end, if you have doubts, you can ask. Yeah, just give me a couple of minutes. I need the co-host access. I've asked them for it. Should be resolved soon. Is my screen visible now?
Yes, sir.
Yeah. Okay. All right. Let's get started now. So first of all, how was quiz 2? Anyone found it very easy, very
Well, sir,
difficult? Sorry? Could you repeat? I couldn't get you.
little bit difficult, sir.
Okay. Okay.
Not so
Any
good.
particular comment that you have? Was it lengthy or was it in what way was it difficult?
To use a Taylor series in that sums that 5 a n squared and a n is tending to infinity, trigonometric functions.
Okay. So there will be one or two hard questions in every exam. That is by design. But I don't think it required the use of Taylor series. That would not be expected. Anyway, a solution file should be shared with you soon, so you can take a look at it then.
Yes, sir.
Maybe if we have time at the end, I'll discuss it too.
Okay, sir.
Okay, then let's get started with week 9 content. So up until week 8, we have seen. In week 9 also, we'll be doing a little bit a continuation of what we did up until week 8, where we talked about functions, limits, continuity, and then differentiability, the tangent lines, and linear approximation, and so on. One of the most applied aspects of calculus is optimization, which means you want to compute the maxima or minima of a given function. So let's start with the following setup. If I have a function, I'm not assuming it is continuous or anything. It could be any function you want. When would I call it a local maximum? Emphasis on the word local. So I'll draw a continuous function or even a smooth function, but the same sort of analysis should be true for even discontinuous function. I'll give an example of a discontinuous function as well. Suppose you take a point like this. Is this a local maximum or a minimum?
No, there is not.
It is not, right?
In the negative x as well.
So you have to look at points in the immediate vicinity of the given point. You have points that are greater, points for which the function value is greater, as well as points for which the function value is lower. More specifically speaking, if I move to the left, I will have the function to have lesser value. And if I move to the right, I'll have that the function will have higher value than whatever it is at this particular A. But what about, let's say, this point? Assume that this is at the apex of this graph. If you look at points in the vicinity, what are the function values when compared to the point that is marked with a cross? Is it lesser in value? With the marked point does it have higher function value or lower function value than nearby points?
That's higher function value.
Yeah, so it has a higher function value. So this is what is called a local maximum, meaning there is a small interval. Now, if I expand the interval and consider, let's say, this interval to this interval, of course, there is a point over here which is higher than this point. So for example, this point is higher than this point. The function value at that point is higher than the function value at this point. So this local part is relevant in the sense that we look at a very small neighborhood around the point. If there is even one small neighborhood, there is another way to write it. There exists epsilon greater than 0 such that f of x, let's say f of a is greater than or equal to f of x for all x in a minus epsilon to a plus epsilon. Do you understand the statement? There is a small neighborhood. So I am free to choose as small an epsilon as I want. But there exists one such that the epsilon neighborhood meaning you go epsilon value to the left and epsilon value to the right. So in either way, you will find the function value to be lesser than or equal to, as an extreme case, if you consider the constant function, every point is a maximum and every point is a minimum. because we don't need it to be strictly greater than. So here, somewhat trivially, every point is a maximum and a minimum. And the same thing, same analysis can be done for even discontinuous functions. So suppose I have something like this, and I have something like, so this point is not included. And I have something like this. This point is included. So let's say this happens at x is equal to 3. Is x is equal to 3 a local maximum or a local minimum, or is it neither?
Neither,
Yes, sir.
maybe, or
So when I look at a neighborhood of 3, is there a, or maybe this was not clear, I'll just do this, right? So is there a point in a small neighborhood of 3 such that a point in that neighborhood is greater?
It is lesser in the left side.
So okay, I'll give you 3 options, right? 3 is a local maximum.
Sir, what is
Three.
the straight line which you have drawn in the right side?
That is the continuation of that function. It's
Oh.
defined some way up to 3, and it is defined differently after 3.
Oh.
So which one of these 3 options is correct?
Local max.
So this is the correct option. And why is that? If I look at the value f of 3, whatever that value is
Greater
nearby
than
points-
left side of.
yeah, it's always greater than or equal to any point in any in a small interval. So you can take, for example, this interval. Any point the function value is less than, in this case, it is actually strictly less than, other than at 3 itself. So it's always less than or equal to f of 3. So this is also a point of local maximum. But we will be looking at differentiable functions and trying to get the conditions using the derivative. So at that point, this you can't. That is why we'll have a different notion of critical points. I'll explain that when we get there.
sir,
So
on the
notion
lower
of-
curve,
Yeah.
sir, on the lower curve, 3 is not included. So still we will say it is the maximum.
Yes. So the function. Okay. Let's give an explicit example. If this is not clear, just one moment. Let's say I have f of x is equal to sin x from x is equal to minus pi to what do I want it to be? Let's give it pi by 2 only. That's fine. So, and over here, and that will become 1. I'll call this, let's say, 2 plus x squared, something like that. So 2 plus x is enough because you are working with a straight line. So until pi, let's keep the interval of definition just from minus pi to pi. Pi by 2 is an interior point for this function. What does the graph of this function look like? Let's try to plot it. So from minus pi all the way up to pi by 2, it follows a sinusoidal curve. So it's this. Yeah, probably pi by 2. Let's just keep it somewhere over here. One full cycle, right? So here, this point is not included. And from pi by 2 to pi, it's some 2 plus x, which is start somewhere over here. And that point, that the height of that point is exactly 2 plus pi by 2. But then it follows a straight line path. Here I wanted it the other way, so I'll do this. Will that work? Let's just do some 10 minus x. That's fine. The value, the exact value of that is not that important. So it'll look something like this. Right?
Yes, sir.
And it's the part where it intersects the x-axis, all of that might not be precise. It might not even intersect the x-axis. It will not intersect the x-axis before it hits pi. So forget about all of that because we are only concerned about the point x is equal to pi by 2. So at the point x is equal to pi by 2, the function value is something like 10 minus pi by 2. Right?
Yes, sir.
And if you look at nearby points, are the function values lesser than or greater than 10 minus pi by 2?
Lesser.
So this is the local maximum, right? That's the definition. So in an interval around that point, that should be the point with the highest value. There should be no point with function value higher than that. That is what is called a local maximum.
Yeah.
So pi by 2 is a local maximum. Is this okay now?
Yeah, yes, sir.
So could you please repeat?
So for the function, for a point to be called a local maximum, what do we need? We need that there is an interval around that point such that the function values in that interval never exceed the function value at the point of interest. So for example, in this case, the point of interest is pi by 2. F of pi by 2 is 10 minus pi by 2 as per the given definition. And there is a small neighborhood. You can take some small epsilon such that for every point in that small neighborhood, the corresponding function values, they will always be less than 10 minus pi by 2. This is visually clear, right? You can actually verify it also algebraically. The sine curve will never go more than 1. So that part of the graph will always be lesser than 10 minus pi by 2. And then you have a negative slope line going downwards. So that will also go more and more, well, lesser and lesser than 10 minus pi by 2. So pi by 2 has an interval around it. There is an interval around pi by 2 such that the function value at pi by 2 is the maximum among all points there. So locally, pi by 2 is the maximum. Is that fine?
Then what would be the ultimate maximum or maxima?
Global maximum in this case will also be pi by 2 itself. But unless you impose certain condition on the domain, which we will see later, you cannot always guarantee that there is a local maximum or a global maximum or a global minimum. We'll see examples of that sort also. But in this case, we're talking only about local maximum. So we're only interested in function value at that point and function value in a neighborhood. And compared to the function values in the neighborhood, the function value at pi by 2 is the highest. So that's why it's called a local maximum.
Okay,
Is that
sir.
fine?
Yes, sir.
Okay. So where were we? Now, okay. The last point is what is important. If f is differentiable, so in this case, f was not differentiable. So this does not apply to that point. For point 3, this is more the representative diagram. Then the tangent to f is parallel to the x-axis at the points of local extrema. So if you have a smoothly varying function and something is a local maximum, what happens? So it's varying smoothly, and then if there is a maximum, then on both sides of the interval and also the minimum. So let me just draw a graph with both behaviors. If this is a point of local maximum, then the function has to be lesser on either side, meaning it has to increase until here and then decrease down there. And if you look at the corresponding tangent line, you will see that the tangent line has to be flat. Similarly, when it goes from decreasing to increasing, the terminology of turning points also was introduced in earlier weeks. You can relate it to that. The tangent has to go flat. Observe that is not the case over here in the discontinuous function, because there you can't even define the tangent line at the point equal to 3, x is equal to 3. Or over here also, you can't define the tangent line at the point x is equal to pi by 2. Why? Because it's not even continuous. It cannot be differentiable. Differentiable implies continuous. Or even more explicitly, if you take that first principle limit, or if you look at the way the graph is there, you can see that the tangent can't be drawn. But in the case that the tangent can be drawn, if a local extremum appears, then the tangent becomes flat, meaning f prime a is equal to 0 at extreme points. At extrema, I'll just call it extreme. Okay. Now, with that in mind, if we have a differentiable function, in order to detect minima or maxima, I know that the only points that I need to consider are the points where the derivative vanishes, right? But what about other points? There might be, so differentiable functions are the nicest class of functions. But sometimes what happens is you have certain behavior until certain point and then certain behavior, and you might encounter a sharp edge where the transition takes place. And those points are also important. And also boundary points, sometimes the function will be defined on a closed interval. And these boundary points are also important. Once again, this will all be clear when I give an example. But considering all these factors, we will call a point to be a critical point if it is either not differentiable at that point, or if the derivative vanishes, right? And the remark here says that whenever you have an extremum, either a local minimum or a local maximum, then that is a critical point. But every critical point need not be a local extremum. For all of these, now we'll see examples, right? So first of all, let's see why we consider. In fact, we have already seen why we consider this as critical points as well. So if this was the function given to me, what are the critical points? Can someone quickly check what the critical points are?
pi by 2 minus pi by 2 and minus 3 pi by 2.
Pi by 2 minus pi by 2 and
Not 3 pi by 2.
just one moment. This is not even the correct graph. No? From minus pi to 0, what is the nature of the graph? It will always be negative. So it's like this. Sorry. Okay. Now, could you let me know what the critical points are?
Pi by 2 and minus pi by 2, sir.
Pi by 2 and minus pi by 2. Are these all? Why? So why are these the critical points?
The graph has maximum and minimum value on these between this domain.
No, so you should not look at the maximum and minimum and call them the critical points. So critical point is an independent definition. The relationship between critical points and maximum, we have not written it down explicitly yet. So what does the definition say over here? You should look for points where the derivative vanishes or for the points where the derivative does not exist. In this domain, at what point does the derivative not exist? Except the boundary points. So let's just look at the interior points. At what point is this function not differentiable?
Pi by 2.
At pi by 2, it's not differentiable. So this is a critical point. Now, at what, so for all of the points, the derivative exists. Let's just look at the interior, open interval minus pi to plus pi. F prime x is cos x for x in this interval. And f prime x is minus 1 for x in this interval. Isn't it?
Yes, sir.
Now, in this interval, where does cos x vanish? At what point does cos x vanish?
Minus pi by 2.
At pi by 2.
So minus pi by 2, it vanishes. Pi by 2 is not there in consideration. Both times I've taken open intervals because
sir, yes, sir.
at the point pi by 2, it's not differentiable. So we have already taken pi by 2 as one of the critical points. Now to look at the other points where the derivative vanishes, we compute the derivative at the other points, which is cos x on one piece and minus 1 on the other piece. So this will never be 0. So the derivative never vanishes at this point. But in this part of the graph, from minus pi to pi by 2, there is only one point at which the derivative vanishes. And that is exactly minus pi by 2. So there are two critical points. Pi by 2, because the function is not differentiable over there. Minus pi by 2, because the function is differentiable and the derivative is 0. And as we were saying earlier, if you look at the point minus pi by 2 and look at the tangent line, it will be horizontal. Right? So the critical points, without talking about minima, maxima, anything, the critical points in this interval are pi by 2 and minus pi by 2 for this particular function. Now, the other example that I want to discuss is f of x is equal to x cubed. So what is the derivative of this?
3x squared.
And let's just take the entire real line as the domain. Now, what are the critical points on the domain?
X equal to 0.
x equal to 0 is the only point because x cube being a polynomial is differentiable. So there is no point where it is not differentiable. So that set of critical points are not there. So the only critical points are when the derivative vanishes or f prime x is equal to 0. But f prime x is 3x squared. So that is 0 only when x is 0. So x is equal to 0 is the only critical point. But now, what we had observed earlier is if f is, let f be differentiable, x naught is a critical point. Sorry, x naught is an extremum, implies f prime at x naught is equal to 0. So if there is a local minimum or a local is a local minimum or a maximum, then the derivative vanishes. So is the converse true? So this is true. What about if f prime x naught is equal to 0, then x naught is a local extremum. Is this true? The answer is no,
Yes.
because look at this function f of x is equal to x cube. The function looks something like this. Right? So look at x is equal to 0. Is it a local maximum or a minimum?
None.
It's not, right? Because to the left of it, the function value is negative. To the right of it, the function value is positive. And at the point, the function value is 0. So there is no neighborhood in which it is the greatest, or there is no neighborhood in which the function value at 0 is the least. So this is not x is equal to 0 is not a local extremum, but it is a critical point. So derivative vanishes does not imply local minima or maxima happens. But if local minima or maxima is true and the derivative exists, then it has to be 0. Is this point clear?
Yes.
Right. So if you have a differentiable function such that a point is a critical point without being a local extremum, as it happens in the case of f of x is equal to x cube at x equal to 0, then such a point is called a saddle point. This is a terminology that we will use. You might be more familiar with point of inflection, and maybe there are some other usages. But in this course, we will be using the term saddle points. The terminology saddle points becomes more clear for functions of two variables, which we'll look at in math 2. For now, that's not important. But the important point is that the derivative can vanish while the function still not being locally maximum or minimum at that point. Okay. So now the thing that we were promising is the following. How do I compute the maximum or a minimum of a function, and how do I classify the critical points? So we said that if f prime a is equal to 0, It could be a maximum, it could be a minimum, it could be neither. So how do we know which case happens? So there are three cases to classify the critical points. Once you obtain the critical points by computing the derivative and equating it to zero, there are three cases. The second derivative is positive, implies that the point is a local minimum. The second derivative is negative, implies that it's a local maximum. And if the second derivative vanishes, then we cannot really say anything. That is the case where this derivative test fails. We cannot classify it as a minimum or a maximum or a saddle point. So once again, examples. Let's take the function f of x is equal to sine x. Find out and classify all the critical points. So we have taken a very simple function just since it's the first function that we're dealing with. Typically, the functions that you'll be given will be harder, but not too hard. You will be able to differentiate it with all the rules of differentiation that you know. Before attempting to do it properly mathematically, let's draw a diagram. The diagram is not the solution, but at least it'll give us an idea of what to look for. So the graph of sine x is something like this. So how many critical points do you think it has? How many minima and how many maxima do you see if you just look at the graphs?
Infinite.
Yeah, so every top of the hill is a maximum. And this happens at pi by 2, 2 pi plus pi by 2, 4 pi plus pi by 2. In general, 2n pi plus pi by 2 for any n. And there are infinitely many integers. So I'll get those many points where it is maximum. Similarly, the other set of points, these points, they happen to be odd multiples of pi by 2. Not exactly odd multiples, right? It's not odd, not just odd multiples. It is like 2n pi minus pi by 2, I think would be correct. Minus pi by 2, 3 pi by 2, and so on. So this would be local maxima. This is what we expect. We have not solved the problem. We have just written down what the graph suggests. Now let's solve the problem. Are there critical points for this function which are not differentiable? As in, are there points where this function is not differentiable? Is sin x a differentiable function? Are trigonometric functions differentiable or
Yes, it is differentiable.
yes?
Yes.
So the class of critical points which are categorized by lack of differentiability do not appear. So we can differentiate and find the critical points. So any point at which the cosine function vanishes is a critical point. And at what points does the cosine function vanish?
When pi
Pi
plus
by
pi
2.
by
Look at pi by 2, 3 pi by 2, whatever pi plus any multiple of pi plus pi by 2. Maybe that is a better n pi plus pi by 2. At all of these points, the cosine function vanishes. Is that fine?
Yes, sir.
Yes, sir.
And this is the set of critical points, because I've said that critical points are points where either the derivative vanishes or you have that the function to be not differentiable, which is not happening over here. So these are the points at which the derivative vanishes, and that's why this is the set of critical points. Now, which of these correspond to minimum and which of these correspond to maximum? Without looking at the graph, if we want to solve it, we'll compute the second derivative of the function. And what is the second derivative of the function? It is negative sin x. So let's take a few candidate points. At pi by 2, f prime is positive or negative?
Negative.
At 3 pi by 2,
Positive.
No, negative.
it's minus sin x.
Yeah,
So
3
it
pi
will
by 2,
be,
sorry.
yeah.
Yeah.
So at minus pi by 2,
Positive.
it's positive. So now if you look at the general term, since you have n pi plus pi by 2, when is n pi plus pi by sine of n pi plus pi by 2, when is it positive? You can formulate those conditions in terms of whether n is odd or even, and you will exactly get this classification. So this is a local, negative means maximum. These two are local minimum. Does this agree with what we have seen over here?
Yes, sir.
Of course, these are some particular values. You can formalize the argument and give the same argument to say that points of the form 2n pi plus pi by 2 are local maxima, and points of the form 2n pi minus pi by 2 are local minima. All right. And in this case, the derivative test is successful. It told us, it gave us full information about all points. But this is not always the case, as we had seen for the case of f of x is equal to x cube. Over here, f prime x is 3x square, which is 0 only at is the only critical point. At x equal to 0 only, this thing vanishes. So this is the only critical point. But if I look at f double prime of x, that is 6x. And f double prime of 0, we have to compute it at the critical point. So this would be 0. 6 times 0 is 0. So the test is inconclusive. So we cannot really conclude whether or not. So one more point to remember is that this does not imply that 0 is a saddle point. Be careful. So it doesn't mean this is minimum. Sorry, this is negative means maximum, positive means minimum, and 0 means saddle point. It's not a saddle point just because f double prime is 0. Just to make that point even clearer, in this case, it is a saddle point. For x cube, it is a saddle point. But consider x to the power 4 if you. In this case, do you know what the graph of this looks like? It is something like a parabola, but it's the growth and the flatness near the origin are even more pronounced. So it looks something like this. So what is x equal to 0? Is it a local minimum or a local maximum?
Minimum.
Local minimum.
It's a local minimum. Right? So everywhere else it's positive. So at 0, of course, it's the minimum. But if you do the derivative test, you will get 4x cubed, which means that x is equal to 0 is the only critical point, and f double prime is 12x squared, which at 0 is 0. So this is a minimum that is not detected by the second derivative test. So second derivative test doesn't work every time, and f double prime 0 equal to 0 is precisely the condition in which it does not work. If it is positive or negative, we can say this happens. And we have gone directly to Riemann sums. There is one more important class of problems. I'll just write it down over here in another page. Computing global minima and maxima.
Sir, excuse me, sir. To find the critical points, we should do the derivative tests and see. Is it like that?
Yes, you have to first rule out the points which are at which the function is not differentiable. All of those are critical points.
Okay, sir.
And then you do the wherever it is differentiable, you do the
The
derivative test.
derivative test. Okay, sir.
Global minima and maxima, together I'll just call them extrema. So as we were discussing earlier, and someone had brought the point up that what is the absolute minimum or maximum? And that is called global extrema, which means that if you take any point on the domain, that is the one with the highest possible value. There is nothing greater than that. There is nothing with a higher value of function than that. So computing global extrema, not always possible. Example is, very simple example is f of x is equal to 1 by x. Or let's just take e to the x, since it's even nicer. On minus infinity to 0. I'll just take this interval. You know the graph of e to the x. And I'm just looking at the negative part of the real line and the function above that part. So you have the function to be something like this point included. Does this have a global maximum?
No.
No.
The global maximum does exist because x is equal to 0 is a maximum. We have included 0 in the domain, and f of 0 is 1. And every other point on the domain, the function value is lesser. Is a local as well as global maximum. The global maximum can occur on a boundary point. That is fine. So there we will just say that a neighborhood would mean a one-sided neighborhood. Maybe this is the point that confused you guys, because there is no neighborhood. There's nothing on the other side. So let me skip that and write it like this: e to the minus x from 0 to minus infinity to 0, and x from 0 to. So in this case, what would the other side of the graph look like?
It's the same mirror image of this graph, sir.
Yeah. So it looks something like this. It's a bad diagram, but what can you do? So this is what it will look like, right? So now is there a global maximum? Now, is it clear
Yes,
that
sir.
x is equal to 0 is a global maximum?
Yeah.
1 is the maximum value the function attains. And that's precisely happens at x is equal to 0. But what about global minimum?
The graph ends at infinity on the both sides, so no minimum, global
Yeah,
minimum.
it will not have a minimum. So what would you need if you want to say that there is a global minimum? You want to say that there is a point in the domain where the function value is least possible. Like there is no other point on the domain with as low of a function value. But no matter what point on the graph you take, there is always a point with the
That is
function
lesser.
value lesser than that, right? If you're on the positive side, you have to just travel to the right. If you're on the negative side, you just travel to the left a little bit, and you'll find a lesser value. So there is no single point. So there's every like the exponential function, the value is always greater than 0, but there is no point at which 0 is actually attained. That's why it's asymptotic to the x-axis, and no matter what point you take, there's always a point with lower function value. So there is no global minimum. Is this point clear?
Yes,
Yes.
sir.
Yes, sir.
Yeah. Another standard example to demonstrate this is f of x is 1 by x. Let's say just on the positive side. The graph of this function will look something like uh, something like this. In this case, you will see neither the global minimum or the global maximum, because the closer you go to 0, the higher the function value gets, and the closer you go to infinity, or the higher the value of x, the closer you are to 0. But there is no point at which the maximum or minimum is attained. And this is not just because there is infinity at the end. This may as well happen for a well-behaved function too, even on bounded intervals. Like even if you don't let x go off, even if you just look at the graph of tan x on minus pi by 2 to pi by 2, what is the graph? It's it goes like this, right? This is once again it's asymptotic to the vertical at pi by 2 and minus pi by 2, meaning you can have a value as like given any value of the function, there is always a value lesser and there's always a value higher. So this also, these two are examples of functions which do not have global extrema necessarily.
கண்ணு
But you
மட்டும்
might
தான்
have
தெரியும்.
noticed. Could you please
முகம்
mute yourself?
அப்படியே அப்படி கிடக்கு.
All right, let's move ahead. But you might have noticed that the reason why we don't have the extrema to exist is because of the open-endedness of the interval that we're considering, right? So there is a result which we will not definitely not prove, but on we'll just state it on a closed interval. Functions of global extreme. So instead of defining it on an open interval, so here, well, here this was not closed and bounded. You can't close off infinity, so it's redundant, but I'll write it anyway. So if you have a comma b, a closed interval, if you have a function like this function will always have a global minima as well as a global maximum. So how to compute it? That we'll see. We have note that we have not assumed that this is going to be continuous or differentiable or anything. We are just saying that if it's a function defined on a closed interval, then it is going to have global extreme. Well, you'll need continuous, sorry. You need continuous, you'll not need differential. Otherwise, you can always send something off to infinity in between. Yeah, you need continuous functions, but not necessarily differentiable. And we'll see how that works. Let's do -1 to 3. This is a prototype example. This function itself is simple, but the important thing to take away is the procedure. I want x plus 1 if x is in between -1 and 0. And I want minus x plus 1 right, and we have it to be between 0 and 3. Here we have done 3. So let's close it off also. So how do we compute the global extrema of this? So first I'll give you the algorithm, and then we'll look at it for this particular function. So whenever you're given a function on a closed interval, these are the steps that you have to follow. Compute the critical points. What does that mean? Points at which it is not differentiable, and the points at which the derivative vanishes if it's differentiable. Then compare function values at all critical points and boundary points. The demonstration, once again with an example, with this example. So we have this this function. We'll draw the graph of it later, just for a change. For now, we'll not draw it in the beginning. We'll do it properly mathematically first, and then we'll see that the graph does verify our computations. So what are the critical points? First, let's talk about that. Anyone? What are the set of critical points? Are there any critical points?
-1?
Well, -1 is not in the interior, so that's a boundary point. We'll not call it a critical point. Is 0 a critical point? If yes, why? So remember what we said about critical points. This has to be either points where the derivative does not exist or where it vanishes. So is there a point in the interior where the derivative vanishes? So first of all, in the open interval -1 to 0, as well as in the open interval 0 to 3, this is a linear function. It's a polynomial function, so it's differentiable. So those points, the derivative exists and you don't have to worry about it. And the derivative will be 1 from -1 to 0 open, and it will be -1 from 0 to 3 open on both sides. So the derivative also does not vanish. So there are no critical points from -1 to 0 open and 0 to 3 open. So the only interior point that I have to worry about is 0. Is this part clear?
Yes, sir.
Okay. Now let us look at 0. Is the function differentiable at 0? Is the function continuous at 0?
So,
Yes, sir.
It's continuous,
The
right?
line.
Because you have 1 as the function value. But what about the nature of the tangent? Is it differentiable?
It's a linear function, so
It is a linear function on both sides, but the join of those linear functions need to be smooth, right? Only then would it be differentiable. For example, if you look at the graph of mod x, that also has linear functions on both sides of 0. But then the point where they join, it becomes a sharp point. So it is not sufficient to say these are linear functions, so it is differentiable. The most proper way to do it would be perhaps to look at this f of 0 plus h minus f of 0 divided by h. To look at differentiability, this is the first principle definition, right? In this case, f of 0 is 1. So you'll have f of h minus 1 divided by h. On the right side, what is f of h? It is minus h plus 1. So look at h appearing from the right, approaching from the right. So in this case, the limit would be -1. From the left, it would be h plus 1 minus 1 divided by h, which is 1. Are these right-hand limit and left-hand limit equal?
no, sir.
No. So this limit does not exist because the right-hand limit and the left-hand limit are not equal. So this is a point where the function is not differentiable. So 0 is a critical point. And this is the only critical point in the interior. Is this part clear?
when we look at the graphs of these two functions, it is a straight line. So
It is a
if
straight
there is
line.
no,
If there is no,
This is
please.
because so these lines are, one is with the positive slope, another one is negative slope, and meeting at this 0 point, yeah? Or
Yes, it's like the inverted, like upside down image of the mod x function. We'll see that.
okay.
So, but just purely theoretically also, you can argue that this limit does not exist. The limit of this as h approaches 0 does not exist, because from the right it is different, from the left it is different. So from the right it is -1 and from left it is +1. So it is a critical point. So now we list out all the points of interest. So the points of interest are critical points and boundary points. Okay, so we have 0, we have -1, and we have 3. This is x. And what are the function values? The corresponding function values, f of 0 is 1. F of -1 is 0. And f of 3 is -2. Is this okay?
Yes, sir.
So which is the global minimum and which is the global maximum? So the algorithm says that the global minimum and maximum will be among these points, among the critical points in the interior or among the boundary points. So now we have the list of the function values, which is the maximum and which is the minimum among them.
-2 is the minimum.
This is the minimum. This is the minimum function value, and it corresponds to x equal to 3. This is global, the point where the global minimum is attained. And what's the maximum?
X is equal to 0.
So this has to be the point where the global maximum is attained. Now let's draw the graph. Things will be clearer. But the thing is, you can't always rely on drawing graphs because the functions are usually not so simple. Even if you have a trigonometric function, you might not be able to draw the graph so easily. So always rely on the robust first principle definitions of stuff, and you will always have this happen at finitely many points, at least for the problems that you'll be given in this course. Right. So now the function from -1 all the way up to 3. So we have 1, 2, 3 roughly. X plus 1. What is the graph of x plus 1? It's a slope 1 line. So it's something like this. What is -x plus 1? Y-intercept is 1 and the slope is -1. So it will be something like this. And one very small thing to note is that you can draw the graph quickly for at least linear lines. If you remember that this is in the slope intercept form, you don't need to worry about where it intersects y-axis, x-axis. You know, you look at this, you say, okay, it's in slope intercept form, it's slope 1, y-intercept 1. You can draw it quickly. Now, does the graphical representation agree with our assessment that x is equal to 0 corresponds to the global maximum and the function value at that point is equal to 1?
Yes, sir.
Yes, right. And that also that the global minimum of the function happens at x is equal to 3, where the function value is -2. It is a boundary point. So there we did not do any derivative analysis. On the boundary points, you don't do it. And on points where it is differentiable, not differentiable, you don't do it. But you list them out anyway and compare the function values at all these points. So you will get that this, the global minimum and maximum, you can just using this procedure. So once again, I'll repeat what procedure you have to do. You have to look at critical points in the interior. Once again, what does critical points mean? Points at which the derivative vanishes if it exists, or if it does not exist, you just consider that a critical point. And then you list out the function values, all the function values at the critical points, and also 2 extra points, which are the 2 endpoints of the interval of definition. So this gives you the global minimum and maximum. And among the all the points listed, you just pick the minimum and maximum. There might be multiple. So you might have something like 1, 0, -2, 1 also. So there might be multiple global maximum that can happen. That is okay, because at all of those things, the function value will be some same thing, right? So you can have multiple, just like if you take sin x, for example, you will have something like this. And let's say I restrict it to some closed interval. You will have multiple maxima and multiple minima, global minima, global maxima. So that's okay. If there are multiple, it's fine, but you will always find the global minimum and maximum this way. And for functions defined this way, piecewise, you should know whether the join is smooth or not. In this case, it's not. So that there it is not differentiable, and you just take it out, take it as a critical point and do the derivative on other points. In this case, the derivatives also turned out to be constants on points other than x is equal to 0. But you might find critical points there also. So you'll probably have this list to be larger. You will have at least 2 points, them being the boundary points, but then you might have critical points also in loop. So even if you look at something like a one-handed derivative, you will see that at the boundary point, it is not vanishing, but still the function can be a minimum there because the interval of definition ends there. A boundary point can be a minimum point. So when you're considering a closed and bounded interval and a continuous function on that, you will always find a global maximum and a global minimum, and it may appear at the boundary also. And this is the algorithm to do that. Is this clear?
Yes, sir.
Yes, sir.
Once again, compute critical points in the interior, write down all the function values at the critical points. In addition to that, you also write down the function values at the boundary. The maximum among the function values corresponds to the global maximum, and the minimum among the function values in that list corresponds to the global minimum. Okay?
Excuse me, sir.
Yeah.
Sir, here -1 and 3, why they are not critical points? Because the function is not differentiable, so it can be treated as critical points.
So critical points, we usually just call interior points as critical points. We like to have a neighborhood in which it is defined. So this is the convention that is followed in the course. So and we'll stick to that. All right.
Okay.
So that is the end of optimization. Now we look at, as the last part of the calculus portion of the course, we have integration. Integration, for those who have already seen it, is usually introduced as the inverse of differentiation. But the classical definition is more geometric, and that also is true that it is the inverse of differentiation. We will see this part as well. But before that, let's take a look at how it is defined. What is something like the first principles definition of integration? First, we'll talk about definite integrals using a particular example. So, and it's not even an explicit example of a function that I will, the expression of which I will write out. I'll just give a picture, right? Suppose this corresponds to x is equal to a, and this corresponds to x is equal to b. So I want to compute this area under the graph. So how do I compute this area? If I don't know anything else, I can start with the following, right? I can look at the minimum value of the function in this interval. So let's say this endpoint corresponds to the minimum value. In fact, using the calculus, the optimization, we can explicitly compute the minimum also by the algorithm that we just defined. Since it's a continuous function on a closed interval, here we have taken a continuous function. As long as it's piecewise continuous also, it's fine. But let's forget about that for now. Look at the area of this triangle that is shaded over here. Is the area of my area under the curve greater or lesser than that?
Greater.
The area under the curve is greater because I've not covered everything. Area of area under the graph is greater than or equal to. I'll just write equal to cover the general case. If it's a constant function, is greater than or equal to area of rectangle, shaded rectangle. Now, what about the other thing? Now, suppose I take the maximum of the function in the interval. Let's have, suppose I have the maximum of the function in the interval. Let it be this blue line. And then I just draw a vertical and compute the area of this. Okay, let's assume that it is passing through that. And if I compute the area of this rectangle, is that area under the graph greater than or equal to or less than or equal to area of this blue rectangle? The blue rectangle goes all the way down to the x-axis, remember. What is the sign that needs to be put there in between?
It's less than.
Less than or equal to. So what we have done is we have estimated the area. We have not given the actual expression of the area, but we have given an estimate. So we have said that it is greater than something, and we have said that it is less than something. This is a rough, this will give you a rough idea that the area of the area under the graph is in between two quantities, which we can compute, which we have not given the explicit computation, but we have said that theoretically it's possible. But now this is not necessarily the best estimate, right? As we usually do, we take sharper and sharper estimates, and we take the limit of that estimates, and we will call that the area of the graph, area under the graph. What do I mean by that? We'll draw this again. Say the whole thing. Copy. Yes. So now instead of doing all of this, I will subdivide the interval right across the middle, let's say. Let's say somewhere over here. Now I'll do the same estimation in this rectangle. So I'll take this rectangle, the lowest value of the function, and this rectangle. and I'll compute this area in these two parts. Similarly, I'll do just in this interval, I'll compute what the highest area is, and just in this interval, I'll compute what the highest area is. And here I will get a better estimate. In this diagram, it might not be clear. The more partitions I do and the more higher and lower estimates that I get, the sharper my estimate will be. Suppose I take a partition of the subinterval, something like this, that there's whatever number of components, 1, 2, 3, 4, 5, 6. If I partition my interval of interest into 6 parts, and then I do the same thing, I do this, somewhere over here, somewhere over here. I take all these small subrectangles, compute their area, and add them up. So if I add the area of this whole thing, which I can do, now that is a better estimate than the one that we started out with, right? The whole, I just take the minimum and compute the area of one single rectangle. This, whatever we did over here, that is a poorer estimate than what we have done over here. The loss of actual area was this part of the graph in the first instance. But over here, it is just this small triangle, whatever looks like a triangle, this, plus this, and this. So it's definitely a sharper estimate. So can you see that if I increase the number of elements in my partition, meaning I take smaller and smaller subrectangles, which constitute A to B, and then look at these estimates, they'll start getting sharper and sharper. Is this a reasonable statement to make?
Yes, sir.
Yes, right? So whenever we want to get information about a general object, what we do is we reduce it to the case of the thing that we know very well. If I want area of a general object, I break that area down into rectangles, and then I compute the area of the rectangles. The area of rectangles is something that we know. So this is the first principal definition of integration. And continuous functions are always integrable, so we'll not worry about whether the limit exists. Here I have written that if the limit exists. So the information in this slide is a little bit overwhelming. So let's go through it carefully. So if I'm given a function defined on a closed interval, given a partition which starts at A and ends at B, similar to what we did over here. So this is just A is equal to x0, x1, x2, so on. So this is x3, x4, x5, and x6. x6 is actually B. More generally, if I have any partition of this form, meaning I just take a bunch of points in between, a finite set of points in starting at A and ending at B. And here I've taken the lowest possible value. So if I take just some random value and compute the rectangle, that's also fine, right? Instead of taking the lowest one, I could have taken any choice of point in between in that given subinterval, in the subrectangle. So each of these are a subrectangle. So x0 to x1 is one subinterval, right? You look over here, x0 to x1 is one subinterval, x1 to x2 is another, x2 to x3 is another. In each of them, you take just one point in between. Some point over here, some point over here, some point over here. Call that xi star. And then compute this product. What is this product? This xi minus 1 is just the length of that interval, right? So if I do x2 minus x1, it is just so let's erase all these things now. Let's keep this guy. For example, x2 minus x1 would be this. Black is not used, so let's do that. It's the length of this component, right? And if I take some function value in between, that is exactly this height. So what this product computes is exactly the area of the rectangle. F of xi star would be the height, and xi minus 1 is the length of the base. So this is the height of the rectangle, and you do it for each of these subrectangles that are defined by the partition. So this is what is called the Riemann sum of f with respect to this partition with the given choice of xi star. The choice of xi star, you can give any choice of xi star. Earlier I was explaining using the least possible value of the function, but you can choose anything in between, because as the length of the subrectangles decreases, it doesn't matter what point you take in between, it will be close enough. But this part, the summand of this summation, is the length of the rectangle. Is this clear?
Yes, sir.
And then when you add the areas of all the rectangles, what you get is what is called the Riemann sum, but geometrically it is the area. It's an estimate for the area under the graph. Here I have to say f greater than or equal to 0, just for consistency. It is required actually that f is a positive function. If it is a negative function also, it's fine. F is greater than 0 is required for the interpretation of it as the area under the graph. I'll talk about it later. So this still makes sense. Even without assuming f greater than or equal to 0, this makes sense. But to interpret it as an estimate for the area under the graph, I need to assume that it is positive. Now,
So,
this is, yeah.
I have a doubt that summation of fxi and the xi minus 1. So
Yes.
those are height and base, right?
Yeah, this
Or
is how we
height
can look
or
at it. Yeah.
so the total that formula is area, right?
This is the area of the subrectangle. Yes.
Okay, okay.
And then you sum it across all the subrectangles. So you'll get an estimate for the area of the area under the graph. It will not be equal. But if I look at the length of each subinterval and I consider, I say that the largest possible length subinterval that you can have in your partition, that is called the size of the partition or the norm of the partition. If I decrease that to 0, meaning I take smaller and smaller intervals. One way to do it is to start out with just one component and then just make 2 components, and then you can make 3 components of the subinterval 4 equal parts. You can keep doing this. Right. So at every step, you will have smaller, larger number of partitions, but each of them with smaller size. So if you keep doing that, what value would this sum reach to? That is what is called the definite Riemann integral of f from a to b. All right, so this is the first principles definition of the definite integral of a function. So that's just what is written in this slide. There we have a function, you have a closed subinterval contained in the domain of that function. Then you can, if the limit exists, you can compute the Riemann integral, the definite integral of the function from a to b. So this is the notation. So this is integral of the function f from a to b. This is how you have to interpret it. That limit is called the definite Riemann integral. This would have been a point where I would want to give an example, which I will maybe in the next session though. Let's get through the theory first. As is usually true with first principles, this may not be the most efficient way to compute it practically. So what we will see next is the interpretation of the integral as the antiderivative and the fundamental theorem of calculus, which allows us to compute the integrals knowing that. So note that we did not define any function corresponding to the given function. We just said that there is this number, which is called the definite integral, which can be computed by taking smaller and smaller partitions, or I should not say smaller partitions, it is finer partitions. If you have to take finer and finer partitions and take that, compute the Riemann sums and take the limit of that sequence. You have to take the limit of this across shrinking subintervals or finer partitions. And whatever value you get, that is called, that real number is called the definite Riemann integral, the definite integral of f from a to b. Now, as I was saying earlier, that there is also an interpretation of the integral as the reverse of differentiation. Now, given any function, I know how to differentiate it, as in not always, but at least as long as it is, at least I know what it means to differentiate a function. Theoretically, at least we know we have to either compute that f of x plus h minus f of x divided by h, take the limit, try to do it by first principle, or use one of the properties, write them as compositions, sums, etc. of known differentiable functions, and then you can say it's differentiable and then compute the derivative using the rules specified. That you can do. But what question we now have or are now going to address is there a function? So if I'm given a function, is this the derivative of some function? For polynomials, of course, you know, right? So is 2x the derivative of a function?
Yes.
Yes.
What function
Yes,
is
sir.
X square.
X square.
it? X squared, right? So this is called the antiderivative. So the derivative of x square is 2x. The antiderivative of 2x is x squared.
X square.
So this is what is called the antiderivative. There is no one way to compute the antiderivative given any random function. But if such a thing exists, we call it an antiderivative. And we call it an antiderivative and not the antiderivative because of the remark below. If I have 2x, your immediate response was x square. But why not x square plus 2? Or x square plus 9, whatever. That might as well.
Because there might be infinite numbers like after x square.
Yeah. So the point is that the antiderivative is not unique. You can add a constant and it will still be an antiderivative because while you're doing the differentiation, constant term, if there is a plus c constant term, then that will contribute nothing to the derivative. So we do use the terminology of the antiderivative, but it is understood that it is said with the knowledge that there could be a difference of a constant. And the notation for the antiderivative is integral f of x without these limits. There are some standard list of examples that you need to know. Sin x is minus cos x. Polynomials, you know. What is integral of, what is the antiderivative of x to the n?
X raised to power n plus 1 upon n plus 1 plus c.
Yeah, this is an antiderivative. This you can keep if you want to cover all possible antiderivatives. This is an antiderivative. So yeah, maybe I should not write this is equal to an antiderivative of this is x to the n plus 1 by n plus 1. So for some standard examples, you will know how to quickly come up with an antiderivative. So how does this help us, or why are we even talking about this? Is the fundamental theorem of calculus, which relates the notion of this definite integral Riemann sum stuff that we had talked about earlier to the notion of antiderivative. We had said earlier that if I take partitions of the interval of definition and then do the Riemann sums, take finer and finer partitions, take the limit, I will get some function. I will get a real number. And by keeping the endpoint of that interval variable, what I can get is a real number corresponding to each point, which is just a function. And that function, which is defined as the definite integral from a to x of f, here, yeah, the variable is t, then that is actually an antiderivative. This is one part of the fundamental theorem of calculus. The other part of the fundamental theorem of calculus, one which is used more often in the actual computation of the antiderivative, the definite integral, is the second part, which is written over here. So if you know the antiderivative of f, then the definite integral from a to b can be computed just by taking f of b minus f of a, the capital F of b minus capital F of a. At this point, we do definitely need an example. So let's get to it. Yes. Let's start off with something simple. F of x is equal to x square on, let's say, x minus 1 to 1. Let's do both definite integral as well as the definite integral. Definite integral, let's compute integral from minus 1 to 1 of f of x dx using 1 Riemann sums. And 2 using fundamental theorem of calculus. Right, so let's go back to the diagram that we were using. That you have the graph of the function at minus 1, it is 1, at 1, it is 1. We want to know this area. We actually don't want to know the area because the Riemann integral is not defined as the area. It's just defined purely formulaically, which we can just compute now. Consider the partition minus 1, 0, 1. And let me take, so here you have two intervals, right? With respect to this partition, you have two intervals, 0 to 1. Let me just take minus half over here and half over here. You will see that this process becomes very tedious very quickly. Because a partition, in order to compute the Riemann sum, I need a partition as well as a choice of a point in each of the subintervals. So this is my choice of the point in both subintervals. So what is the Riemann sum with respect to this data? So for the first interval, I have f of xi star. My chosen point is xi star is minus half times the length of the interval. What is the length of the interval?
One.
Minus
half.
Xi minus xi minus 1. I going from 1 to 2. In this case, we have only two elements. So this is f of minus half times 0 minus minus 1 plus f of half, that is my x2 star. X2 minus x1 is once again 1 minus 0, which is just 1. And what is f of minus half? My function is x squared, right? So it's 1/4. 1/4 plus 1/4. So the whole thing is half. This is one choice of a partition. But I need to keep taking finer and finer partitions, right? So how do I partition -1 to 1 in n parts? For a general n. So this was 2 parts. For n parts, I have to do something like -1 plus 2 by n. And then you have -1 plus is the length of the interval 2 by n? Not 2 by n. It will be, yeah, this should be fine. Yeah. All the way up to -1 plus 2, which is 1. So the last term will be times or n minus 1. And the last term will be n by n, which is just 1. So this is my partition. So what have I done? I have taken this interval -1 to 1, and I want n parts. So look at the length of this interval. The length of this interval is 2. If I want n parts, I have to do -1 plus 2 divided by n should be my increment, so that I get to 1 in n steps. So -1 plus 2 by n, -1 plus 2 by n plus 2 by n, which is -1 plus 4 by n, and so on. So that it might be n plus 1 parts or something, but that's fine. You probably already see why it is so hard, and I'll probably not even complete this computation. You can go and do this. Pick one choice of a point between each of the subintervals, compute this S of Pn. So you will get a sequence of real numbers and check where it converges. You can take this as an exercise. If there is interest and if people think it is worthwhile, I'll solve this in the doubts session. But the
Sir?
important point, yes.
Sir, can you explain how we got the half? Like, I understand it overall, but in this calculation,
This part.
yes, you
So
said
what did we
1/4
do?
part.
Okay, so f of minus half is minus half square. So
Yeah.
the function that I'm starting out with is the square function.
Yeah. I got
Right.
that
So f of
answer.
minus half is 1/4 multiplied by the length of the subinterval is 1. Plus f of half is also 1/4. So you'll have 1/4 plus 1/4, which is half.
Yeah, I got it.
Yeah. Now for n parts, it becomes even more difficult. First of all, you have to look at what the endpoints of the intervals are and then pick a point in between. Compute the function value at that, multiply it with this, compute the function value at that. Okay, it will actually be lesser. Compute the function value over here, multiplied by this, compute the function value over here, multiplied by this, and so on. Somewhere you will go back up, and this is going to happen. So this is a tedious process, but it is, well, theoretically you can say that this is going to give me the answer. But now let us try to do it simply using the fundamental theorem of calculus. What does the fundamental theorem of calculus say? It says if f is an antiderivative of f, then integral, in this case, I'll write the specific function itself. F of b minus f of a, in this case, b is equal to 1. And do you know an antiderivative of x squared?
X cubed by 3.
X cubed by 3. So at 1, x cubed by 3 is 1 by 3.
1 by 3.
1 by
So this is, so let me write this over here in a box, minus, and this is minus 1. So this is 2 by 3. You can verify that if you take n parts, you'll get some sequence corresponding to n, and if you tend that in n to infinity, you will still get the same answer, which is 2 by 3. But it is very difficult, even for a simple function like x squared. Now, what if it is something like sin x, or the sequences that you will get will be even more complicated. So even if you do the equal partition of the interval, this is a very tedious process. But the power of the fundamental theorem of calculus, provided you know at least one antiderivative, then that is not always guaranteed. So you might have a function for which you do not know the antiderivative, and that part is covered partially in the following. So you have certain properties of integrals. The first two are very believable ones. And it is true for definite also. Let me just write that over here. True for definite integrals too. So if I have a scalar multiple of a function, then its definite integral is the scalar multiple of the indefinite integral of the original function. Sums and differences are respected. And the third one is what is more popularly called the product rule. And you may not have seen it in this fashion. Here, there is just I'll edit it when I upload the notes. Don't take it as fg of x or something. Too many x's used. But the point is, let's do a product rule computation. This helps when the function that you have been given, you know the antiderivative of 1, and then if you have something like x e to the x dx, can you just eyeball and see what the antiderivative of this is? What function would differentiate to give you x e to the x? Without doing any computations. So for things like x square, you said the antiderivative is x cubed by 3. You can do that for any x to the n. E to the x, if I give you individually, you will do that. But if I give you the product of x and e to the x, can you come up with an antiderivative on the spot? It might not be that easy. So this is where we use the product rule. I'll write down the product rule again. F G prime. I'll skip the x's, all right. So this is FG. Here it will be FGB minus FGA. So minus A to B F prime G. So when is a good opportunity to use the product rule is something that will come with practice. But usually what happens is if you know that this is the derivative of something and you have a polynomial expression, it is good to use because F prime will reduce the degree of that point. So at least in finitely many steps, you'll get to the answer. So in this case, F of x is equal to x, and G of x is equal to e to the x itself, because what I'm interested in is fg prime, integral of fg prime. Fg prime is also x e to the x itself. So if I want to do 0 to 1 of x e to the x dx, I will do x e to the x at 1 minus at 0 minus 0 to 1. F prime is what? It's just 1. So that goes away. So I get this. What I'm left with is E minus E minus 1. This is 1. Is this okay?
Yes,
So this
sir.
is the product rule. It's not directly product of the integral is integral of the product or something like that. It is more complicated than that. But you will see that this is familiar, right? It's you have fg prime plus f prime g. What is this?
The differentiation of FG.
So that's fg whole prime. So it says that fg is an antiderivative of this guy, which is what is just reformulated and written over here. Right. And then there are some other properties. One is when if you interchange the limits, the value of the integral becomes negative. And the other is you can split the integral. Okay, it should be C to B. Sorry, just type that. Integral A to B can be written as integral A to C plus C to B. It's easy to see when C is in between A and B, but it's not necessary that C is in between A and B. For any C in R, meaning, well, it has to be within the domain. As long as that happens, you can still do that. Most of the time, this is used for computing integrals of piecewise functions. As in, suppose I'm given a function which varies like this or something. So at this point, there is a clear difference. So it would be given as a linear function until this point, and then some other function after that. How do you compute? It will not have a single antiderivative, right? There will not be a single function, or at least a single expression that would differentiate to give you that function. So you break it into two parts, compute the integral of that linear part, compute the integral of that other part if you know it in some way, and then do it. We'll see. I'll do an example for this as well as substitution rule in the doubt session. And now if you have any doubts, you can ask.
Sir, I have a doubt in the example x squared.
In this example, No,
Yeah.
this one.
We did it by Riemann's, yeah.
Yeah.
When we did it by Riemann's sum and
We did
the
not complete it,
antiderivative
so
method.
let me clarify that. We just said this is how we would proceed. Okay. Yeah.
So, we got the answer 1/2 by this method, right?
No, no, no.
This the
So
final
with
answer.
respect to this with respect to the partition -1, 0, 1, the Riemann sum is 1/2. It's not the uh,
The exact
definite
answer.
integral. So to get the definite, complete. So what does complete mean? Obtain. So call this partition as Pn. Okay. Pn is the partition which subdivides the interval -1 to 1 in n parts. So obtain S of Pn. Make a choice of xi star for each of these intervals and then compute the Riemann sum. For example, what we have said is S of P, I guess it's 2. 2. Yeah, S of P2 is half. That is what we have computed over here. P2 is just -1, 0, 1. Right?
So this was not the complete answer, the half.
This is not the complete. So this is an exercise if you want to compute. So obtain this sequence S of Pn. So for each n, you can subdivide the interval -1 to 1 into n parts. Pick a random point in between. I think the prof in his video has done one example explicitly to the end. For since time was short over here, I did not do that. But obtain the sequence S of Pn and then compute S of Pn, the limit. So these are all real numbers, yes? So this is a sequence of real numbers. So I can talk about the limit of this sequence as n tends to infinity. And that number is the Riemann integral. So we did not say just take a partition and so if you recall over here, we did not say take a partition and that itself is your definite integral. If the limit exists, that is called the Riemann integral. So here
And
it says the length of partition goes to 0, and that is the same as saying, at least for this particular sequence, n goes to infinity.
and when we did it by the antiderivative method, so
Yeah.
that answer is the complete answer. Can
That's
we
the
say
correct
that?
answer. Like antiderivative, there is the notion of definite integral of a function is well defined, and both of these are true. What does this theorem say? It says that if I do the antiderivative like this, it has to agree with this. So this Riemann integral, when you're reading the theorem, you read this part as the limit of the Riemann sums. That is actually equal to the difference between the antiderivative values when you look at the endpoints.
Yeah.
So this example was precisely to tell you that even for x square, the computation is very tedious if you do it by the first principle, and to demonstrate the power of the fundamental theorem of calculus. Provided you know the antiderivative. If you don't know, then well, you'll have to something similar to this. If you really want to compute the definite integral of something.
Yeah.
All right. Are there any other doubts? All right then. Let's meet in the next session. I'll compute this last. I'll complete this last topic of substitution, and then we'll take up doubts in that session.
So all the previous recordings, is there any drive link for that?
For the YouTube has on the IITM BS degree program YouTube channel, all the videos should be available.
And like for notes of the classes,
So for the
these
notes, you can
lectures
go
you
to the
took.
portal and there's live session slides under supplementary content.
Okay.
There's a tab
Yeah.
named supplementary contents, and one of the sections in it is live session slides, and there's a Google Drive folder with all the notes there.
These notes you took.
Yeah, these notes will be uploaded there too.
Okay. Thank you.
Yeah. All right. All right then. Bye.
Thank you, sir.